Today we will talk about the periods and groups in the periodic table and the new field. Its name is electron configuration. First of all, this is the periodic table. As you know, we just on the previous lesson we said that we have metals, nonmetals, and metalloids. Actually, we have 8 main groups and we have 8 groups, another 8 groups in the middle. Now, the groups that they have the number, the symbol A, they are main groups, and these groups has a certain name. The first one, it's alkali metals. The second one, alkaline earth metals. Then we have here weak metals, and here I have carbon family, nitrogen family, oxygen family, halogens, and noble gases. The ones down, they have lanthanides and actinides. And the ones in the middle, that they have symbol B, we call them by transition metals. The one down, that they are lanthanides and actinides, we call them by inner transition metals. The most important groups are the groups that they are relative to metals. So the most important groups, they are alkali, alkaline earth, and transition metals. From the nonmetals, the most important groups are the halogens. The word halogen means salt former, something that make a certain salt if I combine it with another metal. And the noble gases, they are the metals that they do not react. And for aluminum and the other metals, we call them by weak metals. These metals, they rarely rust and they are not dense as other metals. Now, on the previous lesson, I mentioned that once we have a certain group, all of the members of the group, they have the same chemical and physical properties, and some of the physical properties, especially if we're talking about metals, because they have constant properties. And I told you that we have 7 main periods, period 1, 2, 3, 4 till 7, and the periods, they deal with electron configuration. Now, what I mean by electron configuration? Actually, miss, when I wanna study about the atom, we study about the nucleus and the surrounding of the atom. If we take the nucleus, it's a certain thing that has protons and neutrons. They are massive, so I can give an indication about the location of a certain proton or a certain neutron. But if we're talking about the electrons, they are particles that they are very tiny. And these particles that they are very tiny, they are not that much massive and they hold a charge. And also because they have a charge, they have a huge amount of energy. That's why in science we cannot predict the location of an element or of an electron. I can give you a certain probability of a location or a possible location for a certain electron. Now, how to determine the location of each electrons? We have many rules that we should follow. The first thing, that each electron has a certain amount of energy. If you remember Bohr's model states that each electron can just orbit around the nucleus with a certain amount of energy, and each electron has its own orbit. This model is something approximately relative to Bohr's model, like how the sun orbits certain planets. Each planet has its own orbit. None of the planets will go to another orbit, none of the planets will leave its orbit. The same thing. But for the planets, because the planets are massive, I can predict its location, while for the electron, never ever can we predict the location of a certain electron, which we call it by quantum physics. The other thing, the electron could be anywhere, as I said. The orbits that they are closer to the nucleus, if we say this is the nucleus, if you are closer to the nucleus, it means that you have less energy. Why less energy? Because the gravity or the attraction of the nucleus will let you to stay in your place. Once you are far away from the nucleus, it means you will have more energy. Each orbit has a certain capacity, we will discuss this now, and the minimum amount of electrons in any orbit that we mentioned should be only 1. And if I have more than 1 electron, the electrons should be like a pair. Each space cannot fill more than a pair of electrons. These pair of electrons, they move in opposite directions. Actually, one of the fun information about in quantum physics, that if we have a pair of electrons or 2 electrons that they are relative to each other, if I put one of them on Earth and the other one on the moon, they will follow the same way or the same mechanism of orbiting. When one of them orbits at a certain time counterclockwise, the other one will orbit at the same time clockwise. They will move in the same direction anywhere we place them. Now, when we are talking about atomic particles, atomic orbits, actually, miss, when we talk about atomic orbits, we have some energy levels. The energy levels, miss, they are actually 7. But for you, I will just mention only 4. Now, these energy levels, we have energy number 1, that's close to the atom, or to the nucleus, then 2, 3, and 4. Now, each one of them, it has a lambda, or something we call it by sublevel. When the level is 1, the one that's close to the atom, the sublevel is only 1. When it's 2, we have 2, and 3, 3, 4, 4, and so on. Now, the maximum number of sublevels are 4 only. Now, what are these sublevels? What types of sublevels we have? The types of sublevels that we have, they are S, P, D, and F. What I mean by this? Actually, miss, when they studied the electrons, they found that once I have a certain orbit, the orbit will have a number of electrons, and these electrons, they move in a certain dimension. If the electron has just a small amount of energy, the electron will follow a dimension of a sphere. So it will be anywhere at this sphere. So the sphere, miss, because it doesn't have certain dimensions, so it will follow, or it will fill only a pair of electrons, so as a maximum 2 electrons. On the other hand, some of the elements or some of the atoms, they have B sublevel. P sublevel can have 6 electrons. How 6 electrons? Because the B sublevel has this shape. So if I want to translate it, I can make it on the x-axis, on the y-axis, and on the z-axis. So each one give you 2 electrons, so it means 2, 4, 6. So I can make 6 shapes, but for the sphere I cannot make only one shape, rather than if I just rotate it around the different orbits. Then we have the D level. The D level, it's like the P level, but it has a certain cylinder in the middle. So even the cylinders, they can give you extra 2 electrons for each dimension. So we will have as a total 10 electrons. The last one, the 14, which is for the F level. Now, so as a summary, if we are in energy level number 1, I have only one sublevel, which is S. If I'm in energy number 2, I have 2 sublevels, which is S and B. So the total number of electrons, 2 plus 6, 8. If I'm at 3, I will have 3 B, 3 S, 3 D, so total 18, and 4, I will have total of 32. Now, there is a certain rule, we call it by Hund's rule. This Hund's rule, we follow it in order to fill the electrons. How we fill the electrons? We have either 2 ways, by using the sublevels or by drawing. Here, the maximum number of electrons are 2, so when I write, if I have 2 electrons, I will write 1s to the power 2. So it means it has 2 electrons. How we draw them? Each one represents a rectangle. I will draw 2 electrons. Here, if I say it will be full, 2s2, 2p6, because the p has 6. So if I want to draw them, this one will have 2, and the 6 will have 6. But how we fill them? Fill energy level with the same spin first. So here I have 6, I will say 1, 2, 3, then I will continue 4, 5, 6. This is the best way. Why we put them like this? Because actually this is the best scenario to let the atom to be stable. The same thing here. Here I have only 1, here I have 3, and here I have 5 to make it 10 electrons. And for this one, we will have 7 rooms or 7 places. Always never ever put 2 electrons in the same direction. If I have an electron that's moving clockwise, the other one should be counterclockwise. This is correct. But if I make them both in the same direction, it will be wrong. Now, if we take a certain example, I will take carbon 6. I will do it again for you. We will say carbon 6. You know that this is the atomic number. Atomic number is the same number as electrons for an atom that is stable. Because it's 6, so I will start. The first one is 1, number n 1. Then we have S, so I can put 2. How many remains electrons? 4. So we will go to the next. 2. 2s. 2. How many remains? 2. After s we have 2p. How many remains? 2. 2, 4, 6. If I want to draw them, this one will be 2, and this one will have 2 electrons, and this one, it has 3 places with 2 electrons only, like this. You can make them both up or both down. Now, what does these numbers represent? This number that it is the n, it represents the period. So here we can say that the carbon is in period 2. The calculation of the number, the last number that you have, 2 and 2, so both of them are 2. The calculation, if you add it, it will be 4. So this is the number of the group. So the group will be 4. If we have a check in the periodic table, you will see this is the carbon. Carbon is in period 2 and in group 4a, as you see here. Actually, miss, the main elements, all of the main elements, none the transition, all of them, they have maximum number, maximum energy number of B. The last energy level is B. While the transition metals here in the middle, the last number will be D. And the ones down, the last number will be F. It will increase as the atomic number increases. Another example here, if we take the neon, neon is 10, 1 is 2, 2 is 2, 2p6. You will see here, because the neon is a noble gas, so we don't have empty spaces. No empty spaces means it's stable. It doesn't need to react. Okay. The last thing that you should follow in order to find a certain way, that this is the way how we can draw them. We can